Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today's session. Okay, so question 1 asks, a 0.10 molar sodium chloride aqueous solution has a higher boiling point than a 0.10 molar magnesium sulfate aqueous solution. Explain why. Okay, so notice that both the sodium chloride and the magnesium sulfide solutions have the same concentration. So that means that in order to figure out why one has a higher boiling point than the other, we need to look at something called the Van Hoft factor. Okay, so I'll just write out how it's spelled. So the Van Hoft factor is the ratio between the actual concentration of particles that are produced when the substance is dissolved and the concentration of a substance, so that same substance, that is calculated from its mass. Okay, so again, it is the ratio between the actual concentration of particles produced when the substance is dissolved and the concentration of a substance calculated from its mass. So it can be expressed using the following formula. So that is an alpha. So here, I is equal to the Van Hoft factor. Alpha is the degree of dissociation. N is the number of ions formed. And over here, if you look at the junior tutor's answer, they have just a table of the expected and observed values of the Van Hoft factor for 0.05 molar solutions of several electrolytes. So they have it for different electrolytes like sodium chloride, magnesium sulfate, iron chloride, hydrochloric acid, and glucose. So they said from table 11.6, magnesium sulfate has an observed Van Hoft factor value of 1.3, while the observed value for sodium chloride is 1.9. Both salts have an expected value of 2. The expected Van Hoft factor value for a salt is determined by assuming 100% of the salt breaks up into separate cations and anions. The magnesium sulfate solution is furthest from the expected Van Hoft factor value because it forms the most combined ion pairs in solution. When sodium chloride is in solution, it has very few combined ion pairs and hence has a Van Hoft factor very close to the expected I value. So this is the reason why it has a higher boiling point. So boiling point elevation depends on 3 variables. The boiling point elevation constant of the solvent. So in the question, they are both in aqueous solutions, so that means they have the same solvent. The Van Hoft factor of the solute, so we can see here that they got different factor values, and the molality of the solution. In this question, molality is held constant. Yep, so I can verify that this solution is correct. Okay, moving on to question number 2. How do you convert tablespoons to grams? Okay, so we would use the conversion factor where 1 tablespoon is equal to 15 milliliters. And also, if we assume the density is equal to 1 mil. Density is equal to 1 gram per milliliter. Then we can also say that when we have 15 mils, this is equal to 15 grams. So it just depends if density is given in the question. If you had a more dense solution, like let's say we had a tablespoon of honey versus a tablespoon of water, then we would know that the water would be 15 grams. But in terms of the honey, it is heavier than the water, so it would probably be around like 17, 18 grams. So it just depends on the density. But by assuming the density is just 1, then we can easily just convert milliliters to grams since they have the same value. So let's see what the junior tutor said. Conversion factors are useful tools when converting one unit to another unit. What we currently have to convert tablespoons to grams are the conversion factors. 1 tablespoon is equal to 15 mils, and 1 milliliter is equal to 1 gram. If you have 15 milliliters of sample, which is equal to 1 tablespoon, this measurement is also equal to grams via 15 mils times 1 gram over 1 mil is equal to 15 grams. This means that in 1 tablespoon, you have 15 grams of the sample. Thus, the conversion factor of a tablespoon to grams can be established as 1 tablespoon is equal to 15 grams. If you have 4 tablespoons, this measurement can be converted in terms of grams using the conversion factor above. Conversion will be as follows. So 4 tablespoons times 15 grams over 1 tablespoon is equal to 60 grams. So the result means that you have 60 grams of the sample on 4 tablespoons. Yep, so I can confirm that this solution is correct. Okay, so on to question number 3. How do you calculate the standard molar enthalpy of formation? So enthalpy, I'll just give a brief definition, is basically like the internal energy of a system. So when we want to find the enthalpy of a reaction, so it can be any reaction like a combustion reaction, or in this case, enthalpy of formation, it would just be the following. So let's say we had just a balanced chemical reaction. So the lowercase letters are the coefficients that are used to balance the reaction, and the uppercase will be that element. So let's say we had this balanced reaction. If I wanted to find the delta H of the reaction, this would be equal to the sum of the delta H of formation for the products minus the sum of the delta H of formation of the reactants. Okay, so now let's try to plug in what these values would look like if I were to use the example of the reaction above. So this would be equal to, first I'm going to look at the sum of the molar enthalpy of formations for all the products. So this is like our elements C and D. And notice that I have an N in front of all of the values as well. So this shows that the coefficients, or how many molecules of each, play a role in calculating the delta H. So for example, this would be lowercase c times the delta H of formation for compound C plus lowercase d times the delta H of formation for compound D. Okay, so this represents the first factor of our equation. All of this will have the delta H of formation sums of all the reactants. So here it'll be lowercase a times the delta H of formation of compound A plus lowercase b times the delta H of formation of compound B. Okay, so this is how you would calculate the standard molar enthalpy of formation. So generally in a question, they'll give you a balanced chemical reaction, and they'll also give you the different delta H of formation for all of the products and reactants that are involved. And then from there, you are able to calculate the standard molar enthalpy of the reaction. Okay, so let's see what the junior tutor said. Enthalpy is a thermodynamic function defined by this equation, where H is equal to E plus PV. E is the internal energy of the system, and pressure and volume, and P and V are the pressure and volume of the system. Enthalpy of reaction is the difference between the enthalpies of the products and the enthalpies of the reactant. Okay, so they have here delta H is equal to the enthalpies of the products minus reactants. Note that we cannot measure the absolute value of the enthalpy of substance and can also determine the values relative to an arbitrary reference. For our purposes, we will use the enthalpy expressions called standard enthalpy of formation. Recall that the standard state is at 1 atm. By convention, we assign delta H of formation of any element in its most stable form as 0. For example, the delta H of formation of O2 is 0, but for O3, it's 142.2 kilojoules per mole. Thus, the definition of delta H of a compound is the heat change that results when 1 mole of a compound is formed from its elements at a pressure of 1 atm. Knowing the standard enthalpy of formation, we can readily calculate the standard enthalpy of reaction given a chemical equation. Okay, so here they just show the general chemical equation that I have also written down, and also the standard enthalpy of reaction equation as well. The generalized equation would be the following. There are two approaches to solving this. We can use the direct method or the indirect method. So I showed the example for the direct method. They also mentioned the indirect method using Hess's law. Hess's law states that when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. This means that if you have a set of reactions, so here they show how one would form a compound AB just by given A2 plus B. So they break it up into different steps. So first is the bond dissociation of A2 to make 2A. The second step is A plus B to make AB. And then they have the final step. So the step 2 is like an intermediate where A2 plus B makes AB. Yep, so if we were to cross out anything that is the same on both sides, then we end up getting the reaction 3. So they say here the enthalpy of reaction 1 and 2 is the same as the enthalpy of reaction 3. So if we just look at 1 and 2, you'll notice that 2A is on the products of reaction 1, and there's a single A as a reactant of reaction 2. So that therefore we can cross out the A in reaction 2, and we can cross out one of the A's there as well. Yep, so I'll just verify that this solution is correct. Okay, so question 4 just asks, what is xenon? So xenon is an example of a noble gas. So this means that it is inert in atmosphere. Xenon has an atomic number equal to 54. So this means that it has 54 protons. So it's a very heavy gas. It is colorless, dense, and also odorless. And xenon is also used in some lamps. But it has relatively little commercial use. Typically, we just mainly use like neon lamps or neon lights, but xenon can be used in some lamps. Okay, so let's see what the junior tutor said. So xenon is one of the elements under the group 8A, which are called the noble gases. Characteristic of a noble gas is its inert property, meaning that these elements are already stable. They will not react to any element to form a compound due to already having a complete 8 electrons in its valence shell. Comparing to other elements on the group 8A, xenon is the second heaviest within the group next to radon. One common application of xenon is in lamp lights. It produces a blue light glow when energized via electricity. Yep, so this solution is correct. Okay, so question 5 says to rank the following compounds by standard molar entropy from highest to lowest. Okay, so first let's define what entropy means. So entropy is a measure of molecular disorder and basically just the randomness of a system. So when you have a system that has a very high entropy value, this means that its forward reaction is spontaneous. So when we have a standard molar entropy, this basically means the entropy of 1 mole of a pure substance under a standard state. Okay, so just another point I'd like to add with standard molar entropy is that when you have a larger and a more complex molecule, these tend to have a higher standard molar entropy. Okay, so because of that point, what we need to do to answer this question is to find all of the different molar masses of each of these compounds. So finding the molar mass of a compound is generally pretty easy since these values can be just found on the periodic table, and we just have to do some basic math in order to figure out how to calculate it. So for example, the molar mass of N2 is just equal to 2 times the molar mass of nitrogen, since there are 2 atoms of nitrogen in N2. So the atomic mass of nitrogen, again, can just be found on the periodic table. It's 14.01 grams per mole. So this gives us a total molar mass of 28.02 grams per mole. We can do the same thing for our next gas, which is just hydrogen gas. So this is equal to 2 times the molar mass of hydrogen. And hydrogen is the lightest element, and it just has a molar mass of 1.01 grams per mole. So its total molar mass is 2.2 grams per mole. And then lastly, we have bigger compound C2H4, which is just ethylene, I believe. So this is equal to 2 times the molar mass of carbon plus 4 times the molar mass of hydrogen. So carbon has a molar mass of 12.01 grams per mole. And again, hydrogen is just 1.01 grams per mole. So its molar mass has a value of 28.05. Okay, so now we can rank these compounds from highest to lowest standard molar entropy. The ethylene has the highest entropy, followed by nitrogen, and then lastly, hydrogen has the lowest standard molar entropy. Okay, so let's see what the junior tutor said. There are 2 aspects of the molecular structure of a substance which affects the value of its entropy. 1, the degree to which the movement of the atoms and molecules in the structure is restricted. The less restricted the movement, the greater the entropy. 2, the mass of the atoms and molecules which are moving. The greater the mass, the larger the entropy. So therefore, since ethylene has the largest molar mass, followed by nitrogen and then hydrogen, the rank of highest to lowest standard molar entropy is C2H4, followed by N2, lastly H2. Yep, so this solution is correct. Okay, so moving on to question 6. What are polar and nonpolar bonds? Okay, so I'll just write out the definitions for both. A nonpolar bond contains two atoms that have equal or even just similar electronegative values. And then I'll just write the definition for a polar bond, which is, as you can assume, the opposite of a nonpolar bond. So the atoms have dissimilar electronegative values. Okay, so I'm going to write out some examples, and I'm also going to just Google an electronegativity value periodic table, just so that we can show all of them. This one's a bit clear. Okay, so I'll have some examples for a nonpolar bond. So nonpolar bonds generally have an electronegativity difference that is equal to 0 to 0.5. So let's say we had a diatomic molecule such as N2. If we were to calculate its electronegativity, its difference in electronegativity for this bond, let's look at our table here. It would be 3.0 minus 3.0, which is equal to 0. So therefore, a nitrogen-nitrogen bond is nonpolar. So let's have another example where we have like a carbon-hydrogen bond. If we were to calculate its difference in electronegativity, carbon is right here, so it has an electronegativity value of 2.5, whereas our hydrogen up here has an electronegativity value of 2.1. So the difference between the two is only 0.4. So therefore, we can say that the carbon-hydrogen bond is also nonpolar. Okay, so let's look at some examples for polar bonds. So when you have a polar bond, basically the difference in electronegativity is around 0.5 to 1.69. And I'll also note that polar bonds are between two nonmetals. Well, any polar bond is between two nonmetals. Same with the nonpolar bond is between two nonmetals. So every time if you see a metal and a nonmetal, this is referred to as an ionic bond. So if you see a metal involved, you already know that it will be ionic. You don't even need to calculate its difference in electronegativity. But going back to the difference in electronegativity for ionic bonds, its difference will be greater than 1.7. So like I mentioned before, atoms have a dissimilar electronegativity values, and because of this, it leads to something called a dipole moment. Okay, so some examples would be like the oxygen-hydrogen bond. If we were to look at its difference in electronegativity, oxygen has an electronegativity value of 3.5, and hydrogen is 2.1. If we were to calculate its difference, it would be 1.4. So therefore, the oxygen-hydrogen bond is polar. So I can draw out a water molecule, and because the oxygen is more electronegative than the hydrogens, it creates a dipole moment in the water molecule, where the sides with the hydrogens are slightly positive and the oxygen is slightly negative. So this is an example of a polar molecule. Okay, so we can look at just one more example of a polar bond. Let's say the phosphorus-fluorine bond. The electronegativity value of fluorine is 4. It is the highest electronegative element on the periodic table. And for phosphorus, it is 2.1. So already we can see that they have a difference of around 1.9. Yep. So this is a very polar bond. So notice that it is between two nonmetals. So let's see what the junior tutor said. The polarity of a bond depends on the relative electronegativities of the two atoms sharing electrons. Electronegativity dictates if the partial transfer of electron density from one atom to another is possible. When the electronegativities are not equal, electrons are not shared equally. This results in the development of partial ionic charges. In definition, the greater the electronegativity difference, the more ionic the bond is. partially ionic bonds are called polar covalent bonds. On the other hand, that having equal share of electron between two atoms and has electronegativity are called nonpolar covalent bonds. Okay, so they have a summary: polar covalent bonds between two nonmetals that have different electronegativities and therefore have unequal sharing of the bonding electron pair. For example, the hydrogen and chlorine bond, electronegativity of chlorine is 3, while that of hydrogen is 2.1. The resulting bond is where an electron pair is more displaced towards the more electronegative atom. The atom with more electronegative gains a partial negative charge, while the less electronegative atom has a partially positive charge. This separation of charge is called the bond dipole. For nonpolar covalent bonds, this is between two nonmetals that have the same electronegativity and therefore have equal sharing of the bonding pair. In hydrogen-hydrogen, they have an electronegativity value of 2.1, therefore the covalent bond between them is considered nonpolar. Yep, so this solution is correct. I'll just also add that for nonpolar bonds, if okay, so I also just added a note that for non-polar covalent bonds, they don't necessarily need to be equal, like exactly equal. They just need to have an electronegativity difference less than 0.5. But the solution is still correct. On to question number 7. What are the quantum numbers of carbon? Okay, so to calculate the quantum numbers of carbon, it is easier to first find the electron configuration of carbon. So let me define electron configuration. This is the distribution of electrons of an atom or molecule in either atomic or molecular orbitals. Okay, so there are different steps to finding electron configuration. The first one is to divide your periodic table into atomic orbitals sections. Okay, so I'm just going to look this up on Google, so it will be easier to see. Okay, so here is an example of how we would divide the periodic table into these different sections. In the blue is the S, the green is the P, orange is D, and this pink is F. So step 2 is to move left to right across the rows starting at H. So this means that we are going to first write the row number, then the block letter. So the block letter is either S, P, D, or F. Okay, so another thing to add, when you get to the D block and the F block, for the D block, we are going to write down the row number -1. And when we get to the F block, it's the row number -2. Okay, so now let's try to look at our example for carbon. Let's move left to right starting at the hydrogen. So hydrogen is up here. It is 1s. Helium is 1s. So I write 1s2 to show that these are the 2 electrons in the 1s orbital. And then moving across brings us to lithium and beryllium in 2s. So this is 2s2. And then moving over to the 2p, we count out 1, 2, up to the carbon. So it has a final electron configuration value of 1s2, 2s2, 2p2. Okay, so now that we know the electron configuration of carbon, we need to figure out the quantum numbers. So one of the rules with quantum numbers is that every electron has a different quantum number, or a different set of quantum numbers. So for carbon in particular, I'm first going to draw out an electron energy filling diagram. And now that I know its electron configuration, I can easily make one showing all the different orbitals. So 1s, 2s, and then 2p. If I were to draw out all of the electrons, there are 2 electrons in the 1s orbital, there are 2 in the 2s orbital, and lastly, there are 2 in the 2p orbital. So both of them are spinning up. So now to find the quantum numbers, n is equal to 2, and this came from the 2 in 2p. And when we want to find our L numbers, this is based on the block letter. So S has an L value of 0, P has an L value of 1, D is 2, and F is 3. So now that we know this, for carbon, its L value is equal to 1. And when you have an L value equal to 1, then its ML value ranges from -1 to +1. And then lastly, for the spin, this can be equal to plus or minus half. So for carbon in particular, if we were to look at the last electron, then its ML value ends at 0, and the electron is spinning up, so it will be positive half. Let's see what the junior tutor said. So first they found the electron configuration of carbon. The principal quantum number is equal to 2. L is equal to 1. ML is the magnetic quantum number, which is equal to 0. And then since it spins up, it has a value of plus half. So I can verify that this solution is correct. Question 8 asks, is boiling water a physical or chemical change? So when we boil water, this is considered a physical change. This is because we aren't changing the molecular structure of water or anything. It is still H2O even in its gas form. So an example of like a chemical change is when it is transformed to one or more different substances. But since when water is boiled, it is just changed to water vapor, this is only a physical change. So the junior tutor said, one indication that a chemical change occurs are new substances found after the reaction. The boiling of water changes its state from liquid to gas if it reached a temperature of 100 degrees. The phase of matter may change, but it is still water. Yep, so the solution is correct. Question 9 asks, which of the disaccharides is not a reducing sugar? So a reducing sugar acts as a reducing agent and this is because it has a free aldehyde or free ketone group when it is in its linear form. So out of all of the disaccharides that they listed, the answer that is not a reducing sugar is the sucrose. So the junior tutor said the answer is C, sucrose. Sucrose is not a reducing sugar. Yep, so the solution is correct. Question 10 asks how many ounces are in 500 mils. So first, let's recall that 1 ounce is equal to 29.57 milliliters. So now let's solve for our unknown. X over 500 is equal to 1 ounce over 29.57 mils. Dividing both or multiplying both sides by 500 mils gives us a final answer of 16.91 ounces. Okay, so the junior tutor said there are exactly 16.91 ounces in 500 milliliters. To convert 500 mils to ounces, we need to keep in mind that 1 fluid ounce is equal to 29.57. Yep, so they also got 16.91 ounces. So this solution is correct. Question 11 asks, 1 gallon is equal to how many quarts? So there are 4 quarts in 1 gallon. Junior tutor said 1 quart is equal to a quarter of a gallon, hence the name quart. Yep, so they also found that there are 4 quarts in a gallon. So the solution is correct. Question 12. How do you convert grams to moles and moles to gram? So everyone's favorite formula, number of moles is equal to mass over molar mass. So as long as we have the molar mass of a compound, we can find the number of moles if we are given mass. Similarly, if we want to find the mass and we are given number of moles, we just need to rearrange the equation to get number of moles times molar mass. So the junior tutor said, to convert the grams to moles, divide the given amount by the corresponding molar mass. So they have an example using water. In contrast, multiply the given number of moles by the molar mass to convert it to grams. Yep, so this solution is correct. Question 13 asks, what is a buffer in chemistry? So a buffer is able to resist changes in pH upon the addition of protons or hydroxides. So the junior tutor said, buffer is a solution that resists drastic change in pH when either protons or hydroxide ions are added. So an example, in the body, we have the bicarbonate buffering system, and this regulates our blood pH. It can be made from a solution of weak acid or base and its salt. It cannot be made directly using a strong acid or base as its salt. Yep, so this solution is correct. What is the difference between electronegativity and electron affinity? So you can see them as kind of like the opposite of each other. Electronegativity is the ability of an atom to gain an electron and on the other hand, electron affinity is the amount of energy released when an electron is added to a neutral atom. Okay, so the junior tutor said, electronegativity refers to the ability of an atom to attract an electron or electron pair. Affinity is the amount of energy released when an electron is added to form a negative ion. Yep, so this solution is correct. And I think we have time for one more quick question. Calculate the number of moles from milliliters. So this can be done in two ways depending on what type of substance you have. So for solutions, we can simply use the equation where concentration is equal to number of moles over volume and rearrange it to solve for moles. And for gases, like ideal gases, we can just use the equation PV is equal to nRT. So if we had the volume of a gas and basically all of the other variables, we could potentially solve for the number of moles as well. Okay, so the junior tutor said, answer depends on what other information is given. So if we had a solution, we can use its molarity, also known as concentration, by manipulating it, so multiplying by the volume. If we are given a gas, we can use the ideal gas equation shown in equation 3. So they also have a scenario if we are given density as well. So if we know that density equals mass over volume, we can use the molar mass of a substance to relate the mass. Okay, so if we are given density, mass, and volume, and we also know the molar mass, then we could also potentially calculate the number of moles just by manipulating some equations as well. So that's an interesting take. So this solution is correct. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you enjoyed today's video, go ahead and give it a thumbs up and a comment, and don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.